Oh, I gotta unfreeze the screen, don't I? Can you guys see the screen okay though? Okay. All right. So today we're going to talk about structures. I'm going to tell you. So I gave you guys an assignment on Friday. I recorded the notes. I didn't. The homework assignment. Basically, what I realized is the homework questions were a little bit harder than the presentation. So I'm going to go over structures for you guys. I did last time. Everybody, take your earbuds out. Put your cell phones away. I did realize that, and then I posted the harder questions because I got some emails over the weekend. Mr. Adams, I don't know how to do number 2. Can you help me with number 4? That's posted in Canvas under the Google Doc. It'll say solutions. You click on it, it'll take you right to my Canva thing. So that's there. So my goal is to go over these notes, give you another day to finish that torque. I saw that some of you did it, but I want to make sure that everybody knows how to do it, okay? So we talk about tension and forces and some of our other things. Don't write this down. These are the terms that we've talked about. Now, some of these we've talked about before, but the short version of it is we want our net force to equal 0, and we want our net torque to equal 0 in some of these structures. I do want you to write this down. So what does that mean? Well, equilibrium is a term that you're going to hear me say today. So in a structure, we want equilibrium. And that's just a fancy word that means that the net force equals 0. It's balance. Equilibrium means that the left-hand side equals the right-hand side, sort of. Okay? Same thing with torque. Now, torque, you've got to remember, and I'll review this, torque has a positive and a negative. But because it's rotational, remember that counterclockwise is positive and then clockwise is negative. And so when we go to do our homework problems, if you haven't finished that assignment yet, or if you want, I encourage you, if you didn't get the best score, to go back over. I thought it was just 6 questions, and I thought, well, and maybe some of you guys Googled some of the formulas and stuff. You'll see that it's just the radius times the force, but then you got to figure out, well, which force? Gravity comes into it. There's tension force, and we've talked about those things before, but I don't think we've ever talked about balancing the torque specifically. Like, we haven't done one example where we balance the torque. And so when I looked at it, I was like, oh yeah, that's, and then I realized after you guys sent me the emails, I was like, oh, maybe I should do some examples where we balance the torque. All right. Now the bottom one here, this is the Greek letter. Well, maybe. Oh, there it is. This is the Greek letter sigma. That is not good at all. All right, we'll try this again. We seem to have some sort of delay. Okay. That is the Greek letter sigma. And I know you guys don't know cursive, but the cursive letter for S, this is regular S, that one you know, but the cursive letter for S is this. And so this is like this is the Greek letter sigma. So it's Greek, which is like R lowercase cursive S. Okay. And that represents, let me move my face out of the way so you guys can see, that represents the stress. So that sigma is stress. And that's just the force that's applied over a cross-sectional area. Okay? And we'll talk about that. Because the cables will have stress. So we're talking about things hanging from cables, suspensions, bridges, stuff like that. I see some of you are still writing, so I'll wait a second. Is everybody done? Can I go to the next slide? Okay. So you don't have to write any of this down. There's a video, you can pull it up on YouTube. But basically, this was a bridge that a wind of 40 miles an hour came along and blew the whole bridge down. Now, sometimes when we have a bad storm, we can experience 30 to 40 mile per hour winds, like a really bad storm. But we've experienced it here in our area. It doesn't have to be a hurricane, right? You can just have a really bad storm. So this was a bridge that was built, and 40 mile per hour winds came along, and it started to twist and vibrate, and it fell down. And they got it on video. This happened in 1940. What's that? I'd have to, well, I don't know. Let me see here. I suppose. Hold on, let me do this. Go to YouTube. I'm sure they have it on YouTube. Tacoma Narrows. I don't know. Let's see if this does. So this is the bridge. And we'll just turn it off. So what happened is when a 40 mile per hour wind came, see how that thing's doing that? Now that is filled with steel cables. And he's trying to record it. So it's a suspension bridge. Now what's funny, if you've ever gone to Mackinac, they have a suspension bridge. That one's a weird one because that's very long. And if you get out there, because it has like you could feel the wind. That one sways a little bit, not much. And Golden Gate Bridge is probably the most known one. Maybe the Brooklyn Bridge too. But we have tons of suspension bridges. But that's what happened. Okay, so we don't want that to happen. So when you design something, the main objective is that it not fall down. Okay, so how do you do that? Well, it's not a joke. You actually try to figure out what will cause the thing to fall down, where it will break, and then you make sure that you make those areas stronger or better. You gotta.
No, I was gonna say, like, wouldn't you want a bridge to be like kind of flexible though?
They do sway a little bit. So I was telling last hour the same thing. Okay, Sears Tower. Well, now they call it Willis Tower, but it sways a little bit towards the top, and we'll talk about that today. But basically, there's an applied torque. Air, wind blows against the whole side of that building, and then up at the top, it creates like a torque, right? Because you have a force that's being applied this way, and it has to stay in the ground, so it kind of does this thing. And so they say it moves like 2 to 3 feet constantly. But they keep that in mind, and we'll talk about I-beams. I-beams are what they use for structures underneath bridges, and that's what they use on those big skyscrapers. They use I-beams, and we'll talk about how those are stronger. But anyways, back to this. We just want to make sure we figure out where it will break, where it will fail, and then what we'll do is we'll make stuff stronger. So let's write this down. And don't write down all the words. Just write down this structure because we're going to do a problem. And so what we're trying to figure out is we're going to have a sign. The sign weighs 50 kilograms. And we're going to create a structure where this could be a chain, this could be a rope, it could be a steel cable. Sorry, got the hiccups. And we know that the angle here is 30 degrees. We know the length from here to here is 2 meters. And basically, we want to know how strong this cable needs to be. So the tension force is the force that's applied to that cable. So really what we want to know is how much force is applied to that cable. Just off the top of my head, and we'll go over this in a little bit more detail in the next slide, the weight of that sign is a force, right? Gravity is pulling down on the weight of that sign, right? The mass of the sign times the acceleration due to gravity, that's the gravitational force that's being applied. Doesn't that create torque right here? Yeah, it creates torque right here. Now that would be clockwise torque, so that would be a negative torque. The other thing is that the cable has to offset that somehow. And believe it or not, the cable does have torque too, because this is a resultant vector which can be broken down into the x and y components. We don't care about the x. The x doesn't really move because this is a structure, right? And we'll talk about that too. This is a fixed pivot point. It's not moving left or right. So because it's not moving left or right, it's balanced in the x direction. So if we were to sum the forces, basically the tension's going this way in the x direction, but also the pulling, the torque will have an application that goes this way. But because it's balanced, we don't even care. Because really what we want to know is how much tension force will be applied to this cable. Okay? I'll just wait till everybody writes that down real quick. All right, here we go. Does everybody have this written down? All right, so we need to figure out the tension in the cable. That's how we make sure that it holds this. So remember, and this you need to write down, the tension is a force that goes towards the wall. It goes back to the wall. Right? If we're thinking about the pivot point, this pivot point right here is going to have a force that goes this way. Now, because, and then also the weight of the sign is going to pull down this way. Well, the tension force can be broken down into its x and y components. And we just do a little geometry there. The tension times cosine of 30, right? That gives us our x component in this direction. And then our y component goes up, and it's just tension times sine of 30. Okay? And we don't want the sign, especially out here at this pivot point, basically we just don't want this to go up or down. So what I'm looking for is that t sine of 30 plus mg, they have to be equal and opposite, right? We want those to balance out to be 0. because the net force in the y direction has to be 0. We don't want it to go up or down. Here I call this a pivot point. It's a pivot for the cable, but it's not a pivot for the sine. So then I want my net torque to equal 0 because they're both applying torque at that point. So let's write this down. Did I go too fast? Everybody have this written down? Can I go to the next slide? Okay. Now? Okay. So here we have two torques. All right? Because the cable has a y component that's going up, it has a torque that goes counterclockwise. Well, remember that torque is just the radius times the force, right? Okay. So that would be, are you writing this down? Okay. So the torque is equal to the radius times the force. And the force that goes up is the tension times sine of 30. Okay. And then we have another force that's going down. Well, that creates a torque that spins clockwise. And it's the radius times the force, but the force is the weight of the sine, which is the mass times the acceleration due to gravity. We want the net torque to equal 0. So this is a positive torque, and the other one would be negative, right? So let me just kind of highlight that. Remember that when we go counterclockwise, that's a positive torque. When we go clockwise, that gives us a negative torque. That's why this is negative here. When we add up all of, and remember this is summation notation, so that means you take the sum of the forces. So what we're doing is we're adding up all the torques, and they should equal 0. That's what we want. Okay? Well, really what we want to know is the tension, right? So here's the thing. I know the radius. I know the mass of the sine. I know the acceleration due to gravity. I even know sine of 30. Whoops. I went ahead too much. So I'm going to do a little algebra to solve for t. So what I want to do is I'm going to move this to the other side. I'm going to say plus r m g. Whatever I do on one side, I have to do to the other. And so I get r t sine of theta is equal to r m g. So to get t by itself, I'm just going to divide by r sine of theta on both sides. And so I end up with, when I do that, this cancels with this cancels with this. I get t equals r m g over r sine of theta. Then my r's will cancel, and so I get mg over sine of theta. That's the tension on that cable. Okay, so we just do a little algebra. I wanted to write out the steps, so I'll give you a second to write down the steps. So there were a couple of homework problems that were very similar to this. Now, we covered tension and X and Y components, and we covered torque. I just don't know if you guys kind of knew how to apply that here. So that's why we're going over this today. Probably, if I would have been here, you guys would have asked me for your homework, help on your homework, and I would have done all this. But we didn't have explicit examples of how to apply making our net torque equal 0. Does everybody have this written down so far? Okay. So now I'm going to clear out the ink. So that's exactly what we do. We plug in the numbers. So just write down the numbers now. When I plug in the numbers, I get that it's 980 newtons. So this way over here, this is T equals 980 newtons. So if I don't have a rope or cable or chain that can hold 980 newtons, what will happen? It'll snap, right? Now, what could I do? Now, we're assuming a lot of things. We're assuming the wind will never blow on that sign. That's not true. So it's not enough just to make the cable or string or rope equal to 980 newtons, right? It has to be stronger than that, right? Well, how much stronger? We could double it. That would be pretty good. We could triple it. I don't know. But that's what we call a safety factor. So this was in your homework too. So safety factors can range anywhere from 2 to 12. What does that mean? That means we're just going to multiply it. So if I wanted to do a safety factor, so this is what I want you to write down. If I wanted to do a safety factor of 5, I take the tension in the rope that I know the rope will be receiving on a regular basis. As soon as I hang that sign, that rope is being pulled 980 newtons. Or cable or chain, depending on what I want to use. So I say, well, I feel comfortable with a safety factor of 5. That just means I'm multiplying 980 newtons times 5. So my design strength for this sign should be 4,900 newtons. Okay? We should have 4,900 newtons tensile strength in whatever I use to hang the sign. And that should be more than enough. That way, if the wind blows, heck, a person could even climb on the sign. I remember a long time ago, it was probably my summer off, I was flipping through the channels, and on one of the C-SPAN channels, there was a court case where a guy tried to break into a vending machine, and he climbed on top. He was trying to steal the money out of the vending of Coca-Cola. I think it was Coke or Pepsi. And he was trying to break into one of the vending machines that was outside, and he couldn't get the door to open, so he climbed on top of the machine and pushed against the wall. And then somehow the machine fell on top of him, and he got injured. So he was suing Pepsi or Coke because they didn't secure the machine to the wall with a cable. And I was fascinated because he was on the stand. He was, yes, I climbed into it and I was trying to break into it, but they should have secured that machine to the wall. No, that's the most ridiculous thing I've ever seen or heard in my life. But a lot of times they settle those things out of court. They probably, Pepsi or Coke wanted to fight it, they'd hire the best attorneys. It'd be like $50,000 to $100,000 in lawyers' fees, or they could just give the guy $10,000, which is all he wanted, anyways. How much money do you think they have in a Pepsi machine or a Coke machine?
Not $10,000.
Not $10,000. So anyway, by the way, none of you guys go climb on top of those machines. All right, back to this. Don't write this down. I just want you to think about this. You could use rope. All right, so these are different working loads or tensile strength. This is how much these items can hold. These are the ones that would work because they're greater than 4,900 newtons. So a 3/8 inch rope would work. An 1/8 inch steel cable would work. An eighth of an inch is very tiny, very tiny. And then you could use chain 6mm. Let's see. This one has an 1/8 of an inch is like, I don't know if I could even show you guys. It's like the second. It's like this little thing. Right? Well, no, I went too far. It's the first kind of long one is an 1/8 of an inch, and then 6 centimeters. Let's see, or is it millimeters? It's 6 marks before you get to the 1. So that's pretty tiny. Anyways, those are the ones that would work because they can hold up to 4,900 newtons. You could even do like the 8mm chain that would hold quite a bit. Well, also the 1/8 inch steel cable would hold it. You don't need to write this down. At some point though, things do break, even steel. So here's what happens. Steel starts off as iron. They heat it up. The heat gives the molecules a little extra energy, and then they push it together. When it cools, those molecules are kind of locked in. Okay? Now, when I pull on a steel cable, I'm pulling those molecules further apart, but there's a molecular structure that holds it in place. If I keep pulling and keep pulling, I can pull harder than that molecular structure wants to keep in place, and that's when the cable snaps. Okay? But there's a point where it stretches a little bit, and that's called elasticity. So steel cables will stretch over time. Bike chains will stretch over time. So they have to keep that in mind. Those suspension bridges have a lot of cables woven together. They go out and check them to see if they've stretched. They don't want them to stretch too much because they'll break. Okay? But they do stretch a little bit. I know in robotics, we use rubber belts, and at the beginning of the season, they're super duper tight. By the end of the season, they've kind of stretched a little bit. Anybody ever shoot rubber bands at somebody? What happens if you hold the rubber band a really long time? It stretches it out, and then when you let go, it doesn't shoot as far. So when you really want to shoot somebody, go and let go quick, right? Same principle. Rubber bands are obviously way more elastic, but a balloon stretches really big, but if you put too much air in it, it'll pop. And that just means that the molecules are getting further and further and further and further away, and then at some point they'll break loose. I don't need you to write down the words. I just need you to kind of sketch this image, and this is talking about tensile strength. So tensile strength, it can be measured in terms of force applied over a cross-sectional area, which is kind of like it's like pressure. So in the last example, what we did is we talked about how much force something can hold, but really there's a certain amount of pressure. Now, in tensile strength, we're talking about what is technically the breaking point of something. So a plain steel, regular just plain steel. So this isn't a steel cable. This is just steel. And so it's like a steel rod. So over here I have this weight that's pulling down, right? And that creates, well, let me jump in here and I'll kind of do like a mock, well, not a mock, but a rough free body diagram. So Right here, you have this mass that's pulling down, and that is mg. Then you have tension that's going up. That tension is a force, right? And then way at the top here, we have that same tension pulling down wherever this cable is mounted right here, okay? And the tension is equal to mg, okay? Now, what they're saying, at some point, that force creates stress based on the cross-sectional area. And if you go beyond, and so the tensile strength is the maximum stress. Okay, so that's the breaking point. So for steel, it's just 250 million newtons per cubic meter. Okay. So those cables do break. They can break. That's why the safety factor is so important, right? So if I choose a safety factor of 5, it's probably never going to break because there was too much weight on it. I'm able to hold 5 times the weight of that sign. I'm never going to hold 5 times the weight of that sign. But if a strong wind comes along, it probably won't make the sign weigh 5 times more. Okay. Can I move on to the next slide? Yeah. Okay, cool. You don't need to write this down, but there's also a compression strength. So like on concrete, think of like a concrete bridge. We have one here in town that goes over the train tracks, right? So if this is concrete and I have a semi truck that goes over the concrete, that's going to push down with mg, the mass of the total truck, right? So that's going to create a force that's being pushed on the concrete. So if it's just concrete, and this is just scientifically measured, kind of. Where's my little thing at? It's 28 million newtons per meters cubed, right? That's just plain concrete. If we put the little reinforcement rods in there, you guys know about the steel rods that they put in there? If they put the little steel reinforcement rods, it's much stronger, okay? Because the steel can hold it, all right? And then the other thing they do, if you notice on the bottom, they use these I-beams, and the I-beam looks like this. And I'll show you in the next slide, those are much stronger. Can I move on to the next slide? Okay. So, well, not the next slide. So this is an example. I just need you to draw the pictures. Okay, we're not going to go through this whole example, but just draw the pictures. So this is like one of your homework problems. So sometimes this is like a window washer, right? And we're trying to figure out what makes this window washing rig safe. Well, 60 kilograms is about 120 plus pounds. It's 132 pounds, actually, just so you can kind of get an idea. And so we want to make sure that the tension on the left cable and the tension on the right cable is strong enough to support the weight of this person. Now, in this problem, this person is creating torque on this side, and they're also creating torque on this side. So we need to think about that. What if the person's standing all the way over here? We probably do the exact same problem, but basically we need to figure out how much tension one of the cables needs. Okay. So what we do is we draw a free body diagram. And in a free body diagram, we're just sketching out the different forces. So the tension force goes up, the tension force goes up, the mass of the person times the acceleration due to gravity applies a force about here. And then the mass of the actual, platform or beam, we could consider that in the center of mass. And so that gets applied here. Okay. Okay, move on to the next slide. I see some people writing down, so I'll just wait. All right, let's move forward. And you don't need to write these down, but these are some simple structures that they use. Bridges can have this, where you have a couple beams. Here you would need to think about the pressure coming down, right? Sometimes they have a truss. A truss is interesting. You're basically taking the weight that's pulling down here and you're creating tension up here. That tension gets shared across this thing, but this is a rigid structure at the top. So there's tension on this structure, so it doesn't move. And because it doesn't move, then this structure can't move, which means it kind of holds everything together. And so the links on a truss actually certain links go through tension, and some of them go through compression. Some of them are compressed, depending on where they're placed. But it redistributes that gravitational force across the structure. You do need to write this down, though. So rigid bodies such as posts and beams can exert compression, tension, and shear force. Okay? Tension is stretching, compression is pushing something together, and shearing, it moves left to right. So if we think about the post of a bridge, there can be some tension. Maybe a wind comes along underneath the bridge and pushes it up. The compression comes from the cars driving over the bridge. And the shearing causes the bridge to sway left to right. And there's lots of things that could cause that. In the video that we saw at the beginning, that was caused by wind. Wind came along and moved it left to right. Okay. Ooh. It's only Tuesday. You know what I realized? Spring break is right around the corner. Oh, it's in March sometime. It's actually like 2 months away, but it's more like a month and a half. Are you guys getting kind of tired of school? Yeah. February, March are tough months. But after spring break, you're like, oh, we only have a couple months left of school. And then when it starts to get warm out and the sun's shining, winters in the Midwest are kind of, I don't want to say depressing, but it's like, it's definitely like a low. All right, can I move on to the next slide? Nope, not yet. Okay, I'll wait. How about now? Okay. Don't write all the words. I just want you to write the picture, sort of. Yeah. Well, I definitely want you to sketch out the picture and write everything here. So I want you to just write this down. And we don't need this stuff. Don't write that down. Don't write this down. Because I'm going to say those words while you're sketching it out. Notice that the cross-sectional area is the same. So a solid square beam can hold 440 kilograms. That's the max load that can take. And this is it's about, it's almost 2 inches. A little bit more than 2 inches, actually. Probably might be close to 2.5 inches. Not quite 2.5. Probably like 2.25 inches. I don't know off the top of my head, but it's just a little bit longer than 2 inches by 2 inches, this little square. So the cross-sectional area then is going to be 27 centimeters squared. And so that solid square beam can hold 440 kilograms, which is a lot. You know, it's like 1,000 pounds. But now an I-beam, notice that it has the exact same cross-sectional area. So it's the same amount of material, but because it's an I-beam, it can actually have a max load of 2,340 kilograms, which is 5 times stronger. So if you go to any bridge, look up at the bottom of the bridge. It's all constructed with I-beams. It can handle all of the shearing. It can handle the shearing. It can handle the compression. It can handle the tension. Does everybody have that written down? Okay, cool. Now, some structures, and you don't have to write this down, just look at the screen. Ropes are good with tension. Ropes and cables are good with tension. All right? So that bridge that we watched at the beginning, it had steel cables for sure. But you could see where the steel cables were, they were swinging all the time. This is going to sound weird, but the bridge wasn't heavy enough. So when the bridge moved a little bit, could the cables hold it in place? No, because the cables were designed to hold the bridge, But when the wind came along and blew under the bridge literally would, so the cables couldn't handle compression, and compression could come from the bottom pushing up. And the cables aren't very good at holding the shear. So if the wind blew the bridge a little bit this way, and a little bit of the wind got under the bridge, it would cause it to do this. And the cables couldn't really stop it. There was no structure for the cables to actually stop it. Now, if you look at the Golden Gate Bridge, or more modern ones, it has like some structures, I-beams specifically, that can handle that up and down. And they're heavier, so the weight on the cables kind of holds it in place because they have safety factors. Probably what they did with that first bridge, they probably had like a safety factor of 2, right? Well, sometimes you need more than that, okay? I don't know. I'd have to research it a little bit. You don't have to write this down either, but ropes and chains always transmit forces along a line of their length. So if I have a rigid rope, that tension force goes to where it's attached. If I have a rigid steel beam, that force is applied going towards where it's mounted. That's a tension force. Okay. Now this I do want you to write down everything. Okay, so write down the words. And this is like a breakdown. This is a breakdown of what you're seeing. So basically there's a weight, okay, and it's 10 kilograms. It has a mass of 10 kilograms, but the weight of a 10 kilogram mass, remember to find the weight in the physics class is the mass of the object times the acceleration due to gravity. So gravity is pulling down on this 10 kilogram object with a force of 98 newtons. But when it comes to structures, we have to consider where all the forces are. They all transfer, they all cancel. So if you start at the top, if you start over here at the top, okay, right here, this little hook is being pulled down at 98 newtons. So this has to be anchored in here really, really well, enough to hold 98 newtons. Then if you look at the rope has 2 connections. This connection right here is being pulled at 98 newtons, okay? And then, but it's also being pulled downward at 98 newtons. Then if you go to the other connection, where it's connected to the weight, it's being pulled up 98 newtons and being pulled down 98 newtons. The weight itself is being pulled up by 98 newtons, but it's also being pulled down 98 newtons. So this is technically being transferred all the way up here. So a lot of times when we have these structures that are pulling cables or steel cables or compression, whatever the case is, it's a transfer of that force from one object to another, usually connected through some rigid structure. This is a rope, which isn't a rigid structure, but by the nature of us pulling the rope tight, it transfers the force. Okay. Now, at any point in the rope, or if we use chains, or if we use cable, at any point in there, what we'll run into is equal tension or equal force, right? So the only time a rope would break or a chain would break is because you have an issue. So if it breaks right here, if it's a steel cable, it could be rust, right? And if it's a chain, maybe it's a bad weld because they weld those chain links And if it's rope, maybe it's frayed. Okay. And so that's what you'll see something break. Now sometimes it'll if it's the same force throughout the whole thing, it's kind of hard to predict, but there'll be a weaker part. So whatever the justification is, this is where am I at? I'm way over here, aren't I? No. So this is weaker. Oops. What the heck is going on? All right, can I move on to the next thingy? Move my face out of the way. You don't need to write this down. Basically, they're talking about in the real world when you go to do these things, sometimes where it's attached, there's frictionless attachments. Where, in other words, we don't worry about the force. Most of the time, there's a normal force, but there has to be an equilibrium of forces, right? So if I go to the next slide, if there's friction that holds this thing in place, that has to be accounted for. If it's not going through a surface, then there's a normal force. These are reactionary forces. So if I'm pulling from a wall this way, that means that I'm pulling from the wall this way, which means there has to be a force that's going in the opposite direction because these structures don't move. So we have to balance. In other words, if you add up all the x direction forces, that equals 0. If you add up all the y direction forces, that equals 0. And if there's torque and you add up all the torques, they have to equal 0 because the object isn't going to move. We don't want it to move. That's basically what it's saying. And here's the example with the torque. Okay. So now I do want you to write this down. So this is also very similar to some of your homework questions. So sketch this out. I'm going to need some room here, so we'll put this over here. And I'm going to have you guys sketch some additional things too. So remember that, whoops, don't look at that. Nope, I want the pointer. I want my pen. All right, let's try this. Remember that torque is equal to the radius of an object times the force that's applied across that radius. Okay? Also remember that for this object to remain stationary, the torque has to equal 0. So here we have a structure, and I have a radius here. We'll call this R1 equals 2 meters. And then we have a force that equals 1,000 newtons. Let me change the color. So we have two torque forces. Change this to blue. Then I have another radius and that's 5 meters. We'll call that radius 2. And then we have another force pulling down. Now that force is the mass of this object, m, which we don't know what it is yet, times the acceleration due to gravity. So we'll call this torque 2. And torque 2 is, the blue one is going this way. And my other torque, this torque here, is going this way. So the one that's going counterclockwise is positive, and the one that's going the opposite direction is going to be negative. So if I were to write this out, I would say plus R1 times the tension force, right? So this is my torque, and it's positive. Then the next torque would be negative, and then that would be R2 times mg, right? And that whole thing has to equal 0. So this is like my torque 1. Well, let me... So this is like my first torque. That's all my stuff in red. And then this is like my second torque. And because we don't want this thing to move up or down, those torques have to be balanced. And by the way, this is the last thing we're doing, so if you guys are getting a little antsy. Okay. So then what do? Well, let's solve for, I know R1, I know the tension, I know R2, I know the acceleration due to gravity. I don't know the mass. But I could do algebra and figure this out. So what I'm going to do is I'm going to say R1 times T minus R2 times M times G is equal to 0. Next step, I'm going to add R2 mg to both sides. Just going to do a little algebra here. And I get R1 times tension is equal to R2. Oh, wait. I totally screwed up. Don't do that. Don't do that. Yeah. Screw that one up. The last problem I solved for T. This one we're going to solve for M. So what I need to do, remember I got to solve for M because we want to know the mass. So I'm going to actually... Actually, you know what? That's not a bad idea because I want a positive mass. So if you erased everything, I'm sorry. Oh. Well, we'll just go with it. So let's do let's just go ahead and do it. So I'll say minus R1 times T is equal to minus R1 times T on both sides. That gives me negative R2 mg is equal to negative R1 T. Now, if I multiply everything by negative 1, everything becomes positive. So this is R2 mg is equal to R1 T. I want to get m by itself, so that means I have to divide everything by R2 and G. This cancels with this cancels with this, and so I'm left with m is equal to R1 times T divided by R2 times G. So then I just plug in the numbers. R1 is 2 meters times the tension, which is 1,000 newtons, divided by R2, which is 5 meters, times the acceleration due to gravity, which is 9.8 meters per second squared. These meters cancels with these meters, and we're going to have some wonky stuff. Let's do the math on that. So if I pull up Desmos, I really want to show you guys how to use the Desmos calculator. This is embedded in your the SAT, which you guys will take in a couple months. So if I click this little fraction thingy here, and I say 2 times 1,000, then on the bottom I say 5 times 9.8. And I hit enter. It's about 41 kilograms, right? If I round that. So I'll make my little squiggly line here. So my mass, this thing here, the mass up here is about 41 kilograms. Any questions on that? How do you guys feel about this type of work? Could you do one of these problems on the test? Okay. So maybe we need a little more practice. So what I'm going to do is I'm going to stop right here. I'll give you a little more time to go back and look at those homework problems. Hopefully this will help you guys. Okay. Let me double check. Yeah, still got it. See how I did that? All right. We're not going to do that one today. Maybe we'll do that tomorrow.